Today we got to kind of picture something. This is the wrong one. I got to bring up this one. All right. Today we're talking about basically spinning. Spinning around a circle, because we started labeling a circle with degrees, started labeling it with radians. Now let's talk about speed going around a circle. And if you look down there, we have like a merry-go-round kind of thing in the picture down there we'll get to in just a second. There's Ferris wheels in there, there's drill bits, basically anything that revolves around a circle, clocks, all that kind of stuff. When we're talking about this, so we're doing linear and angular velocity of rotating objects. Well, velocity is just the speed of something in a given direction. But when we're talking about rotating, there are two possible velocities. There's angular velocity and linear velocity. We'll go through the definition and we'll talk a little bit more about what that means. Linear velocity is kind of like our day-to-day stuff. What your speedometer says, that's your linear velocity. That is just the rate which an object moves or travels, and in this case, it's going to be along a circular path in 1 unit of time. When we're talking about linear velocity, we're talking about miles per hour. Your car, if you drove your car around in a circle, right? And any time you're really driving your car, you know your speed. Miles per hour, it shows up right there. We're still talking about the same thing. What is that speed of that car actually going? Angular velocity is the rate at which an object rotates or turns about a fixed point in 1 unit of time. Now, angular velocity, I'm talking about like revolutions per minute. I don't care how fast I'm moving out here, this second hand will always take a full minute to do 1 revolution. So angular velocity, the tip is revolutions per minute type thing. These are actual speeds like miles per hour, feet per second, anything like that. And we'll talk a little more about that in just a second if it's still a little confusing. So on that clock, 2 motions are happening. We have angular velocity and linear velocity. Now we're going to put this towards a carousel. We're riding a carousel, the worst carousel ever, because there's only 2 horses on it. And you can't quite see it, but there's a black one right here. It doesn't really show up on the printout, but there's a black one there. And here's kind of the above view of it. So we have 2 horses on a carousel. Awesome. One horse, that is the black horse, is only 1 meter away from the center. The white horse is 2 meters around the center. Now I'm going to say this carousel takes, we'll say 2 minutes. Is that about a carousel? Oh, is that too slow? Too slow? All right. 30 seconds. All right. Maybe it's a really big one. Maybe it's not meters. Maybe it's like, I don't know. All right. We'll say 30 seconds. We'll go 1 minute because it's just easier to keep 1 minute in our head. All right. We'll say it takes 1 minute. It goes really slow. It's your little kid one. It takes 1 minute for this carousel to go all the way around. All right. Can you picture that? This carousel is just going around. It takes about a minute to get across. The first thing we're going to talk about is angular velocity. Remember, angular velocity is like rotations per minute. So this carousel goes around once per minute. Keeping that in mind, using angular velocity, which horse is moving faster per angular velocity? If angular velocity is always rotations or something per time. Yeah?
It'd be moving at the same rate in terms of angular velocity.
Okay, so we have same. Any other guesses? Yeah.
The black one?
The black one's moving faster. Any other guesses? There's only one other possibility. Fritz? The white one? All right. Who thinks it's the white one going faster? Who thinks the black one's going faster? Who thinks that they're moving the exact same speed? Grace, you can't raise your hand for both. Just keep your hand raised for all of them. Nailed it. According to angular velocity, they're moving at the exact same speed because angular velocity is revolutions over time. And if the carousel takes 1 revolution per minute, the white one's going to go in 1 minute make it all the way around. And the black one, in 1 minute, going to get around. They can't go faster because they're chained to this thing, right? Does that make sense? Why they're both the same? So in this regards, which horse has the greater angular velocity? They're going to move the exact same. So they're going to be the same. They're going to move the exact same. It will take the same amount of time to make one revolution. It will take the same amount of time to make one revolution. And here's a great, because this is only one of our first days in the class. I wrote that. That's all I wrote. Does that mean that's all you should write? No, you need to write what makes sense. I talked a lot about this. If I just write same, maybe you knew it from the beginning, in which case you could just put same. I'm like, I knew that in the beginning. But if you're stuck at all, put something down. That angular velocity, something like, it's going to take the same amount of time to go around anything of the stuff I said. So just because I'm not writing stuff down doesn't mean you don't need to be. Linear velocity. Which one's going faster according to linear velocity? The white horse. Well, we only have black horse. There's only one other option? Both. All right, let's put it to a vote. White horse is moving faster according to linear velocity. Hands up for black horse is going the fastest according to linear velocity. Hands up for they're both moving the same speed. I'm going to try to convince all of you guys without actually giving you the answer. It takes 1 minute to get around this circle, right? So it takes 1 minute for this thing to go all the way around. 1 minute. In 1 minute, the white horse has to travel that distance. In that same 1 minute, that black horse has to move that distance. Which one has to move faster in that 1 minute time? Yeah. So which horse has to be moving faster? They both have 1 minute to get to the same destination, and one has to go further. Who thinks it's the white horse that's going faster? Who thinks it's the black horse going faster? Who's too busy writing down notes to raise their hand? All right. It's the white horse. The white horse has a lot more ground to cover. So white horse. And something like this is what I kind of put in my notes, kind of generalize that. I said the white one, it covers the greatest distance in the same amount of time. Kind of like when you're, remember those little spinny things that you play on as kids? Maybe not. I don't know. They used to have these things that you could spin each other on.
At the park?
Yeah, at the park.
Yeah.
And if you're kind of close to the center, it's not bad. When you get down to the end, like you can go flying off. Yeah. Same thing. You have to move a lot faster out here than you do inside because you're closer to the center. Out here, you have to move that whole amount of space. Is this kind of making sense at the very least? All right. I think the big key is angular, we're thinking revolutions. And with linear, we're thinking miles per hour. How fast is the wind going through my hair kind of thing. All right, formulas, because formulas are fun. Each one of these problems is pretty much going to follow the same pattern. We're going to find something, do something else, and then perchance do something else. But it's like 3 big steps that we're going to do. I'm going to circle the major ones you need to know for this section. That guy and that guy. In fact, I'm going to start talking about this guy here. That is our formula for finding angular velocity. That is our formula for angular velocity. Well, angular velocity, which is omega, is theta over t, where theta is the angle of rotation in radians the object moves during time t, where t is your time. So remember when I said that carousel went 1 revolution per minute? 1 revolution is almost our theta. We would just have to put it in radians and that would be angular velocity. All right, I just need to change that 1 revolution to radians. Before we get there, how many radians are there in one rotation? In one circle, I guess might be Gracie? 2 pi. Yeah, 2 pi. Pi is pretty important, right? 1 is 2, 1 is 6 points. Yeah. All right, 2 pi. That's going to come in a second. All right, so our problems most likely will give us revolutions. We'll have to turn it to radians. We throw it up there and put it over time, and we have our angular velocity. The next part of our problem is going to say what velocity are they actually traveling at. Well, remember that white horse and black horse? They're both revolving at the same angular velocity, but one's going faster than the other. The only difference between the two is how far away they are from the circle. So when we're calculating linear velocity, the only addition to angular velocity we're going to do is radius. Because the further you are away from that circle, the faster you're going to be going. So once you know your angular velocity, all you need to know is your radius. Radius, I'll point to the right thing. And you know your linear velocity. So once again, most of these problems are you'll know the revolutions per time. You'll put in radians, which will get you that. And then you just have to find the radius, and you're done for a lot of these problems. It sounds easy until we start doing it. All right, questions so far? We okay? No one's mind blew up and they just quit yet. Okay, because it gets kind of easier after. I think there's a nice pattern to these problems. All right, Adam the ant, who's sitting on the second hand of a clock that is 12 centimeters from the center. So Adam the ant, somewhere on here, about 12 centimeters off, just going for a ride. I'm going to preface this first question, which I'll never ask this again, for the most part. See how it says, what is his angular velocity in revolutions per minute? If I go back to here, angular velocity needs to be in radians. Angular velocity will always be in radians unless I specifically tell you don't do that. And the only reason why I'm telling you not to do this is because we're going to build up to how we normally do these problems. All right? So 99.9999999% of the time, angular velocity will always be in radians. And it'll make more sense once we do this problem when I work backwards at where we started from. All right, it says angular velocity in revolutions per minute. So angular velocity is our omega, where we have theta over time. Well, theta is usually in radians. This time we're just going to use revolutions. This one of the few times we're going to use revolutions. So I want some kind of number of revolutions per some amount of time. Now, a lot of times we can do a lot of things. We can say how many times a minute hand goes around, or second hand goes around in an hour. But I'd rather see how many rotations does the second hand do in 1 minute. How many times does the second hand go around the clock in 1 minute? Just hold up how many fingers you think. There we go. We got some ones up. It is 1 revolution per 1 minute. A more simple way to put it sometimes is people will do that 1 revolution per minute. I don't really care because that's not our answer. It's just something we're going to be using in a second. Our next thing, this is usually where we jump. We usually just skip this step and go right to here. This says put that angular velocity in radians per minute. I'll talk about why we have to use radians in a second, but we're going to convert it to radians. So right now we have omega equals, or angular velocity equals 1 revolution per 1 minute. Gracie was nice enough to tell us that each circle is 2 pi radians. So for every revolution, I go around 2 pi units. So either we can kind of replace this, but I'm going to use that dimensional analysis thing where I just say, well, 2 pi radians over 1 revolution. 2 pi equals 1 revolution. This just comes from when I'm converting inches to feet or something like that, where we do that 12 inches per 1 foot. Our revolutions would cancel out, and we'd be left with 2 pi radians per minute. In short, we just came up with revolutions per time multiplied by 2 pi. That's all we did. And then some stuff canceled out. All right, but every time it's going to work this way. I'll give you revolutions. You'll multiply it by 2 pi, and you'll now have it in radians. All right, we now have it in radians. That's 2 pi radians per minute. The next question is, what is the linear velocity in centimeters per minute? Well, it's good. We're talking about centimeters. We're talking about minutes, so we just have to get our velocity. Recall that velocity equals the radius times our angular velocity. And that has to be in radians. And we'll talk about why it has to be in radians and we can't use degrees for this. I know the angular velocity. The thing I don't know is the radius. What is the radius in this problem? What was that?
12 centimeters.
It is 12 centimeters because that ant is 12 centimeters away from the center, right? It is 12 centimeters from the center. So our radius in this problem is 12 centimeters. So we have 12 centimeters times, and we have 2 pi radians per 1 minute. Now we just plug this in our calculator because you'd want approximation. Because when you're driving, you don't say I'm driving 3 pi miles per hour. You give a quick approximation. So go ahead and plug it in. You should get out about, I shouldn't have equals, I should have about 6.28 radians per minute. Did I get something else? Am I looking at the wrong one? Yeah, I copied on the wrong one. Good thing there's lots of confused faces. Does 75.40 sound a little better? And that is going to be centimeters per minute. I just copied on the wrong one. And let's talk about why it's centimeters per minute. Centimeters comes from here. It goes to the top. Minutes go here. They go here. Why is this important? Because I was going to get to, for those of you that care why we have to have radians, this only works with radians because of this step. Do you see radians right here? Technically speaking, I didn't show how they canceled out. So if these don't cancel out, this would have to say centimeter radians per minute, which would be funky and not anything good. These radians actually cancel out. Because if you remember from when we talked about radians, a radian was actually the distance of a radius. It uses a radius to calculate your radians. This 12 centimeters is per 1 radius. Your radius and your radians would cancel out. I don't ever do this because it's kind of a weird way to do it, but that's 1 radius and radians cancel out. That's why you cannot do this with degrees, because degrees aren't based upon your radius. You have to have a whole much more complex formula for degrees. That's why you have to use radians so they cancel out, and we're just left with that. Now we go back to the people that don't care about that. This is how you do it. It works. Trust me. All right, that's why we use radians. All right. All right, we have 75.4 centimeters per minute. Did I lose anyone along the way minus my little spiel about why we have to use radians here? Okay, then we go to the next one. Adam crawls to a point that's 5 centimeters from the center. What are his angular and linear velocity now? We always start with our angular velocity. And we're going to do it in radians. Do I have to do any calculating?
No, because it's the same.
No, because it's the exact same. No matter where he is on that minute hand or second hand, it's going to take him a full minute to get all the way around. So no matter how close or far he is, our angular velocity is going to be that 2 pi radians per minute. It'll be the exact same no matter where he is on that second hand. It still takes 1 minute for him to revolve. So it still takes 1 minute for him to revolve. All right, our linear velocity is going to change because our new radius is that 5 centimeters. And now we do 5 centimeters times that 2 pi. I guess we should have that radians per minute. Our radians kind of secretively negate each other, and we're going to be left with about, I should have about, and plug it in to check, about 31.42 centimeters per minute. Does that match what you got in your calculators? If you did in your calculator, if you didn't, it probably won't match. All right, one more question. Adam's still on the move. Now he's at the very center of the clock. What is his angular velocity? Keeping in mind that he's still spinning. He's just doing this, so he's still revolving. What is his angular velocity now?
When the angular velocity, wait. Yeah, when the hang, oh, wait a minute. Never mind.
It won't be 0 because he's still spinning. Angular velocity is how long does it take for him to do a revolution.
Oh,
So he's...
It would still be 1 revolution per minute, but his linear velocity would be 0.
His linear velocity will be 0, but his angular velocity will be the exact same. It'll still be that 1 revolution per minute, which is that 2 pi radians per minute. Are we all okay with that? No matter where Adam is on that minute hand, he will always be rotating at the same speed. So his angular velocity is going to equal 2 pi radians per minute. Now he's not actually covering any ground, so that's why his linear velocity is 0. If you did not recognize that, if you were just strictly doing the math behind this, the math supports it as well because your velocity equals your radius. He is on the center, so his radius is 0 centimeters. It'd be 0 centimeters times 2 pi, which equals 0. So either you thought through it and said, well, he's not traveling anywhere, so it's 0. Or you actually did the math, which supports he is not moving forward. He's just spinning around in a circle. Whew. You feeling okay? Doing it? We're making it through? All right, cool. All right, how long is this class? Okay, till 25. What are the angular velocity, what are the angular velocity in radians per second and the linear velocity in miles per hour of the trip of a 22-inch lawnmower blade that is rotating at 2,500 revolutions per minute? Cool. Angular velocity. They already gave us a huge chunk of our angular velocity. They said there's 2,500 revolutions per minute. So when I'm looking at angular velocity, I'm automatically thinking of that rotation speed, so I'm going to write that down. I'm going to write down 2,500 revolutions per 1 minute. But what do I need to convert that to in order to work in this formula?
You have to convert it
So it contains pi. So we're going to convert it to radians. Which to put in radians, we just need to multiply it by 2 pi. We just have to multiply it by 2 pi. I'm going to do the whole thing, but when you get good at this, you're just going to multiply this number by 2 pi and just have your answer. But I'm going to do the whole setup where we have 2 pi radians over 1 minute, which equals 5,000 pi radians. I said 5,000, but I wrote 500. I wonder if there's a difference. Pi radians per 1 minute. Here's a problem before I move on. I currently have it in radians per minute. It says it needs to be in radians per second. On a test, I would most likely put it up here, and I'd probably also put it here if I was making you calculate. I'd probably put like a little radians per second. So you realize that we need to convert. Right now it's radians per minute. I want radians per second. So that means I need to get rid of the minutes. This is how I always think about this. I'm like, I need to get rid of minutes. So we need minutes on top over here so they cancel out. I'm trying to go to seconds. And now I'll fill in my information. There is 1 minute per 60 seconds. I went ahead and rounded this because otherwise we're going to have kind of a weird fraction, and we know we're going to round it later on anyway. So this is fine to, at any stage, it's really okay to round. And I always go to the 100th place. So this should round to, plug in your calculators, make sure I'm right. But we should have 261.8 radians per second. Now it matches up with that. Unit conversion should be the hardest part of these problems. Because look at all the work I did. I wrote down a number they did, and I multiplied it by 2 pi. The only thought process I really had to do is how do I get to seconds then? Or calculator read that. Are we all okay with that? So what we learned today is only read revolutions per minute, multiply it by 2 pi. And we have our angular velocity. Sometimes you have to do conversion to do it. Linear velocity. What do I need to find for linear velocity? What's the only thing? We already have angular velocity. What's the other thing we need to know? Yeah. Radius. We need to find a radius. That's it. I just need radius and angular velocity. Already got the angular velocity. I hope the radius is somewhere in here, otherwise I can't do the problem. I'm going to draw a picture. Because people aren't quite sure what I mean by the lawnmower blade. So you have one of those push mowers, right? You just start it up like that. It's got a blade spinning on the bottom. This is looking, I turned mine over, and this is the underneath part of it. Our blade is going to look something like, I don't know, like that. Well, that's a big blade on that side. So this is our blade. It covers our whole circle. So if our blade is 22 inches, so that means its radius must be 11 inches. If you get on the test, and I put something like this on there, and you don't know, if you're not sure if it's the diameter or the radius, just ask. If you're asking which is the radius, I already know you're looking for the right thing. That's what I care about, that you're looking for the radius, that you're not just taking any number up there. I'd much rather you ask than just guess, and then I'm not sure what you're doing. All right, so our radius is 11 centimeters. So all we have to do to get our linear velocity is take v, and that's going to equal our 11 inches multiplied by that angular velocity we had, which was 261.8. I guess I'll put radians per second. And we now have, what did that round out to be? 28,000. Not 28,000, I'm sorry. 2,879.8 inches per second. It wants linear velocity in miles per hour. It wants it in miles per hour. So I put that big step right here. We're going to convert it to miles per hour together. All right, we'll go step by step. There's lots of stuff we have to do. I'm going to do the units first, and then we'll do everything else second. So we're converting it to miles per hour. So we already have, guess what? We already have the bulk of our points. All right, on a test, most of our points are done. I'm just give you a half point or another point, depending how big the problem is for this section. And most of the time, as long as you attempt it, you get half the points for this too. Your big chunks are, this is where most of the points, if you're doing this problem on the test, huge chunk of your points right here. A little bit is converting these because I'm teaching you this. This is just a skill. Huge point in knowing how to do this. The conversions are just a small part of it. So if you're really confused about the conversions, don't spend all night tearing out your hair because you can't convert feet to miles or something like that. Worry more about memorizing and knowing these formulas. That's worth a lot more points. That being said, let's go ahead and convert this. So we started with 2,879.8 inches per second. I need to get to miles per hour. Let's do inches to miles first. So what I'm thinking about, I can go from inches to feet. I can go from feet to miles. So I'm going to write that stuff down. Inches have to go there so they cancel out. And feet have to go there so I have that. Well, inches will cancel out. Now I just have to say what makes sense in this. Well, we have 1 foot per 12 inches. All right, now we have to go from feet to miles. Once again, I'm going to put feet down here so they cancel out. And I'll put miles up here. 1 mile equals, who knows?
I think 5,200 something.
80. 5,280. Want to know how to remember that? Just remember the old saying, 5 tomatoes. When you're converting miles to feet, you need 5 tomatoes. You just need 5 tomatoes to remember miles and feet. You laugh, but I still remember that from high school. All right, so we have 5 tomatoes, feet per mile. We are now in miles. We are now miles. Now all I have to do is put seconds to hours. You can do it in one step. You can do seconds to hours if you know there's 3,600 seconds per hour. But a lot of times we'll just do seconds to minutes and then minutes to hours. I don't care which method you use. I'm going to go ahead and do seconds to hours. So we'll do, seconds to minutes. So we'll have 60 seconds per 1 minute. That means our seconds would cancel out. And now we just do minutes to hours. 60 minutes to 1 hour. I'm going to tell you the easiest way to do this. You can simplify. You can multiply all the way across, write that number down. Multiply all the way across, write that number down, but a little more rapid, especially when you're on a big test or something like that. This times this times this. Hit enter in your calculator. Divide by this. Hit enter. Divide by this. Hit enter. and you'll have your answer. It saves you time. A lot of times on tests, that's all you really need is time. Otherwise, you panic. So once again, just multiply the top, divide by this, hit enter, divide by that, hit enter, and you should get out the right answer. And I came out with 163.6 miles per hour. Did someone else get that? Okay, at least one person did. I'm not terribly off.